In this concept, we're going to answer the question, how do we actually use epsilon and delta? We're going to learn how to take a query and add a certain degree of noise to make what we call a randomized mechanism. And we want this randomized mechanism to satisfy a certain degree of differential privacy. We want to augment a query like a sum, threshold, mean, or average, and add a certain amount of noise to this query so that we get a certain amount of differential privacy. In particular, we're going to leave behind the local differential privacy previously discussed and instead opt for global differential privacy. As I mentioned earlier, the difference between local and global is that global differential privacy adds noise to the output of a query, while local differential privacy adds noise to each data input to the query. So, given that we're going for a global DP, we're adding noise to the output. And how much noise should we add? We're going to add the minimum amount required to satisfy a certain level of epsilon and delta, which we will term our privacy budget for a given query. Now, in order to do this, there are two types of noise we could add, as I mentioned earlier, Gaussian noise or Laplacian noise. Generally speaking, Laplacian noise works better, but technically both are still valid and can give us varying levels of epsilon and delta privacy. In this case, we're going to exclusively focus on Laplacian. Now to the hard question, how much noise should we add? The amount of noise necessary to add to the output of a query is a function of four things. First, the amount of noise is dependent on the type of noise that we're adding. We're just going to focus on Laplacian here, so that one's easy. Second, we must take into account the sensitivity of the query that we are using to query the database. As mentioned, some queries are way more sensitive to removing a person from the database than other queries, and some sensitivity is very consistent sensitivity, as in every database always has the same level of sensitivity for that query type, whereas some queries have varying levels of sensitivity that is dependent on the database. And then, of course, the two other things we must take into account is the desired epsilon and delta. Thus, for each type of noise that we're adding, we have a different way of calculating how much noise to add as a function of the sensitivity of the query to meet a certain epsilon delta constraint. So to restate this, each noise type has a specific function which tells us how much noise to add given a certain sensitivity, epsilon, and delta. For Laplacian noise, this function is the following. Laplacian noise takes an input parameter beta, which determines how significant the noise is. We set the beta by taking the sensitivity of the query and dividing it by the epsilon that we want to achieve. As it happens, delta is always 0 for Laplacian noise, so we can just ignore it. In other words, if we set beta to be this value when creating our Laplacian noise, then we know we will have a privacy leakage which is less than or equal to a certain amount of epsilon. Furthermore, the nice thing about Laplacian noise is that we don't have to worry about delta because it's always set to 0. Gaussian noise has non-zero delta, which is why it's somewhat less desirable. Thus, we're using Laplacian for this exercise. There's this really awesome proof for why this is the case, but that proof is not necessary to know how to use Laplacian noise. Furthermore, when reading literature about differential privacy, you'll hear the term Laplacian mechanism, which refers to a function being augmented with Laplacian noise in this way, forming the mechanism im in the original differential privacy function discussed earlier. The thing we need to know here, however, is that we can take any query for which we have a measure of sensitivity, choose any arbitrary epsilon budget that we want to preserve, and we can add the appropriate amount of Laplacian noise to the output of the query. Pretty neat. In the next project, I want you to do this yourself. First, modify a query for sum with the appropriate amount of Laplacian noise so that you can satisfy a certain epsilon delta constraint. So this new sum query should automatically add the appropriate noise given an arbitrary epsilon level. For Laplace, you can use the Laplace function mp.random.Laplace. After you have this mechanism working for the sum function, I then want you to do the same thing for the mean function, scaling the Laplacian noise correctly given the fact that mean has a different level of sensitivity than sum.
So in this lesson, we're going to learn about how to take a query and add varying amounts of noise so that it satisfies a certain degree of differential privacy. In particular, we're going to leave behind the local differential privacy we previously discussed and instead opt to focus on global differential privacy. So as you may remember, since global differential privacy adds noise to the output of the query, in this lesson we're going to focus on learning how much noise we should add to the output of the query so that it satisfies a certain epsilon delta differential privacy threshold based on the formula that we learned in the last lesson. So now the question is, how much noise should we add? Well, the amount of noise necessary to add to the output of the query is a function of 4 different things. The first is the type of noise that we want to use. The most common types are Gaussian or Laplacian noise, which are simply just 2 different kinds of distributions that we can sample random numbers from. The second is the sensitivity of the query or function that we're adding the noise to the output of, right? So if we're adding noise to the output of a sum query that might have a sensitivity of 1, then that would cause us to add a certain degree of noise. But if we're adding noise to a different query that has a different sensitivity, then we would add a different amount of noise, right? The third thing is the desired level of epsilon that we want to make sure that our next query is beneath. And fourth, the desired delta that we want to stay beneath. So these are our constraints on the amount of privacy leakage that we want to allow. And then this is the sensitivity or the kind of function that we're adding noise to the output of, and this is the type of noise that we're adding to. And with these 4 things, we can figure out how much noise we should add and actually properly build a randomized mechanism. So thus, for each type of noise we're adding, we have a different way of calculating how much to add as a function of sensitivity, epsilon, and delta. We're going to focus on Laplacian noise. So Laplacian noise is increase and decrease according to a scale parameter beta. And before I continue, there are a wide variety of different kinds of randomized mechanisms. In this course, we're only going to go through a small handful of them, and I highly encourage you, when you do finish this course, to Google around and learn some more about the different kinds of differentially private randomized mechanisms that can be appropriate for different use cases. Okay, so back to Laplacian noise. So Laplacian noise is the amount of noise that you're adding for a Laplacian distribution is increased or decreased according to a scale parameter beta. And we choose beta based on the following formula. B, or beta, equals the sensitivity of our query, that's the query that we're adding this noise to, divided by epsilon, right? And this is epsilon, again, we're spending this epsilon for every query, right? So if we're querying a database, right, every time we do it, we're going to spend this amount of epsilon, right? And so the notion here is that we have a certain epsilon budget that we want to stay underneath, and that by using this simple formula, we can know how much noise we have to add to the output of these queries in order to make sure that we are preserving privacy. So, in other words, if we set b this value, then we know that we'll have a privacy leakage of less than or equal to epsilon. And the nice thing about Laplacian noise is that it actually guarantees that we do this with a delta that is equal to 0. Right? So remember we had these 4 things right here. So type of noise, sensitivity, epsilon, and delta. Laplacian noise always has a delta that's 0. So if you remember, delta was the probability that we would accidentally leak more than this amount of epsilon, right? So Laplacian is guaranteed to not leak more than this amount of epsilon. Cool? Now, one other question you might have. What happens if we want to query repeatedly? Well, as it happens, if we do query repeatedly, then we can simply add the epsilons across the different queries. So if we have epsilon of, say, 5, we can do 5 queries that leak epsilon of value 1, for example. This is how sort of the Laplacian mechanism works. In the next section, what I would like for you to do is actually perform a sum and a mean query. Right, so you're going to take the sum and the mean query over the database. These are the ones we used previously in the course. And I want you to add a certain amount of Laplacian noise to the output so that you're underneath a certain level of epsilon. And in the next lesson, I'll show you how I would do this. See you then.